Yep.
Okay, so let's get started. Let's see, does anybody remember the goals of this course, what we're studying here? And for all of you who have forgotten, it's written down here at the bottom of the screen, Professor Bri-Mathias Hodge. He is a professor of electrical and computer and energy engineering. And you're probably wondering, what does this have to do with networks? What does it have to do with cybersecurity? And what does it have to do with technology? And today, Professor Perigo met Professor Hodge. They're just down the hall within 30 feet of each other. And of course, they suddenly realized, my goodness, there are all kinds of exciting things that are relating to software-defined networks and energy systems and smart sensors. And so we are pleased to have Professor Hodge. But here's the thing. He is no, I can't say he's an interesting person, can I? He's a very interesting person. He's just joined the University of Colorado Boulder, I believe in August. So just like you, he's new. And he's on an interesting learning curve. But today, he's going to tell you things about being a RACI fellow. He's going to tell you about some of his experiences at the National Renewable Energy Lab. And in general, you're going to learn about technology, cybersecurity. Okay. I think you know why you're doing what you're doing. Thank you. Professor Hodge, please welcome him.
Well, thanks so much, Professor Curry, for the kind introduction. And I am going to talk about technology, specifically power generating technologies. I'm going to talk about cybersecurity a bit as well and the implications that has on the power system. And then we'll see how much policy we can fit in there as well. So in addition to being a professor here, I also still do work at NREL, so at the National Renewable Energy Lab just down the road, I don't know, about 20 miles in Golden. And there I'm the chief scientist for power systems engineering. And so a lot of the work I'm going to talk about today actually happened at NREL and is still ongoing at NREL. So I'm giving you fresh off the presses research stuff here. The vast majority of stuff I'm going to talk about today hasn't even been published yet. Some of it is very, very new. And so, yeah, I'm really excited to talk to you about what we've been doing and hopefully hear some good feedback on new ideas that we can take that as well. Okay, so first I want to give you a bit of power system background. So as Professor Curry mentioned, the power system is a very big network, right? It's actually a number of different intersecting networks, and we're going to talk about that in a little bit as well. But I think it's important just to understand some basics about the power system and how it works, how it's changing, in order to see the implications that cybersecurity and information technology is having on the power system at the moment and where that's going to go. Just looking at the big picture, in total U.S. energy consumption, you have a lot of different primary sources. So, for example, petroleum fuels a lot of the transportation industry, and you have nuclear power, wind, geothermal, natural gas. This is the electricity sector. So it's a very big component of that. It supplies most of the residential energy, most of the commercial energy, a bit of the industrial energy. And with transportation, it's starting to take over some of that as well with electric vehicles. And so as we're looking toward a future in which we're trying to reduce greenhouse gases, the electricity system is seen as sort of the linchpin of that. So a lot of the generation technologies that you can utilize to produce carbon-free energy are very mature technologies. Some of the applications that you want to do for industrial and transportation don't have nearly as mature technologies, and so we speak a lot about the electrification of society as one of the steps that we need in order to move toward a carbon-free overall economy. And so the electricity generation is going to play a big role in that, and so wind and solar are going to play a very big role in that as well. Because the power system is very difficult. You have to be able to meet supply and demand continuously and instantaneously. So, and by instantaneously, I mean at milliseconds or less timescales. And we're going to talk about some simulations that look at the impact of changes in supply and demand at the millisecond sort of timescale. And you want to do this both reliably and economically. So in the United States, we have very high reliability standards for the power system. At the transmission scale, the idea is you will have less than 1 day of outages every 10 years. So we have such a complex network that reaches from coast to coast, goes all the way from consumers at very low voltage levels all the way up to generators at very high voltage levels. That's a difficult thing to do, and we require a lot of different technologies working in concert to get there. So let me just show you this picture of the conventional power system. So this is how the power system was designed, how it's supposed to work until recently. You have these large generators, whether that's hydropower, nuclear, coal, natural gas, and you generate power there. You step up the voltage so that you can transport it long distances with minimal losses over transmission lines. And then once you get closer to the customers, you step the voltage down, and then finally you step down even further as you get the line to your house, right? And so you have high voltages to reduce losses, keep going down in voltage levels. Now, this part of the system is very big and very intermeshed. So there's a lot of redundancy there. But the distribution system is not so. It's much more of a radial topology, and so it has larger impacts from single point failures. And so I'm going to talk quite a bit today about distribution in the first project I'll talk about, and how we're creating new synthetic distribution networks so that we can do better modeling on this. And then the second part is going to talk about the transmission level impacts of some cybersecurity issues that could happen. Okay, so just as a different graphic to show you how big the power system is and how complex of a network is, this is the transmission system in the United States. So this is above about 115 kilovolts. And so this is the backbone of the transmission system. And you have probably 10 to 20 times more than that on the distribution system as well. So the whole system is split up into essentially 3 interconnections, which are synchronous with each other. That means they're all producing at the same frequency. And it's basically the eastern interconnection, the western interconnection, and Texas. Because that's a sort of policy issue, because if you don't go over state lines, then FERC, the Federal Energy Regulatory Commission, has less say over you, and so they've chosen to sort of wall themselves off like that to not have to deal with quite as many of the policy issues that FERC has involved. So that's 160,000 miles of high voltage transmission lines in the US. So this is a very complex system. The Eastern Interconnection in the US is the largest synchronous power system in the world, and it's often seen as the most complex system ever designed. But it's changing, and it's changing very rapidly. So you have the traditional system, and what's the goal of the traditional system? It's to supply load, right? So I want to use power, and I'm here. How do I do that? Well, I import power from the rest of the system, right? I produce it with, say, a thermal technology. It gets shipped over to me. When I turn on the light, it goes on. It's done that mostly with thermal systems, but also with hydropower, nuclear power, things like that. However, we're rapidly gaining a lot of new technologies on the system. Things like solar photovoltaics, things like wind energy, things like concentrating solar power. And this is changing how the system is operated and how it must be designed. A lot of these, so these are all large plants that are connected at the transmission system. We're also seeing a lot of power on the distribution system. So rooftop PV, like the 6 kilowatts on my roof, right? Now, Xcel Energy, our local utility, knows nothing about that. They, I do an interconnection with them. They don't know how much I'm producing. They don't know if I turn it off. They can't see it because they don't have enough sensors on the distribution system. And so that makes changing the system a lot tougher, because traditionally in the US, you have load and it goes up and down, and then you have generation and you make the generation meet the load. Now, I spent some time working in India, and for those of you from India, you need to flip this paradigm, because in India, you have generation and you run it flat out, and then you turn on and off load to meet that. But it's the same problem, right? You have one control switch and you have one variable that you're trying to chase. The problem is we're now putting more generation on the system, And so we need to be able to change both of those. We need to be able to use all of the switches at our availability in order to control the system and operate it reliably and economically. This changes even more when you add in things like storage to the system, and potentially storage that's behind the meter at the distribution level that the utility also doesn't know what it's doing. And so that makes the system much more complex. Then we add in things like transportation. We start increasing the amount of demand we're going to have because of electric vehicles. Again, I don't have to tell Excel when I want to charge my vehicle, and yet that's a huge load on the system. And so we have this very complex system that's changing rapidly at the moment. And so it's a really exciting time in power systems. This is the generation profile by source that we've seen over the sort of history last 60, 70 years in the power system. And what you see is that coal was a dominant technology for a long time, but that's really dropping off at the moment for a number of reasons. One, because it's economic, and two, also because of policy reasons, regulations, so Clean Air Act and things of that nature. We've had a lot of natural gas generation too, and that's increased dramatically over the last few years. So most of the new generation in the US is either natural gas or wind or solar. And a lot of that has to do with shale gas, right? So shale gas made the prices of natural gas drop, and so you're seeing a lot more natural gas generation than we have previously. Then you have nuclear here, which has remained pretty steady. We haven't built a new nuclear plant in the United States since the 1970s. And so that's pretty constant. And then we have renewables. Now, that renewables looks pretty big, doesn't it? But that's because hydropower accounts there. So hydropower accounts in the US for about 6 to 10% of the power generation, depending on whether it was a wet year, dry year, things like that. But also in there is wind and solar, and those have been increasing dramatically. So wind generation in the US has gone from essentially nothing in 2000 up to now 80 gigawatts of installed capacity. So just for reference, a nuclear plant is about 1 gigawatt, right? So an enormous nuclear plant, we have 80 of those installed in the US in wind turbines. Now this, on a power basis in 2016, produced about 5.6% of US electricity. It's up to about 7% or so now. And worldwide, we now have about 550 gigawatts of wind installed out of a total generation capacity of about 6,500 gigawatts. Now, you may look at these numbers and say, why is it such a low share then? And this is one of the fundamental differences of wind and solar from thermal units. You can't control them to the same degree, right? If the wind's not blowing, you're not going to produce power. And so capacity factors of nuclear plants, they like to keep those very high, 90% or so. So you're producing 90% of your maximum power over the course of a year. Wind plants in good locations have capacity factors of about 40%. Solar PV in good locations have capacity factors of about 20%. So you have a lot more variability, and we'll talk about that more in a little bit. Now, US solar electricity has climbed at an even faster rate. So even in 2010, you had virtually no PV in the United States. In 2016, you had 42 gigawatts. So this now produces about 2% of total US power production, and it's increasing very dramatically. Why is it increasing? Simply put, for a long time, it was driven by policy, by state renewable energy mandates, goals, targets. For example, Hawaii wants to get to 100% renewable energy by 2045. California is in the process of the same thing. So I believe it's just been passed in the legislature, but not signed by the governor yet. And so that's been the driver for about the last 10 years. However, that's all changed. That's been tremendously successful. And the prices of wind and solar energy are now even or even less than most of the thermal generating technologies in most locations. We see this here locally even. Xcel Energy just put out bids for their long-term planning, and the renewables came in far below the cost of pretty much anything else. Even solar with storage combined, and storage has been dropping dramatically in terms of cost as well, comes in less than most of the other generating plants. And so this is going to be the driver for increased amounts of wind and solar power in the future. But as I mentioned, they're different, right? You can't just turn it on, run it at 100%, and let it go. So this is, over a course of about a week, the power output you get out of a 300 megawatt plant here in Colorado. So you see times when it's producing nothing, and times when it's producing almost full power. And it goes up and down. I work on forecasting some, and this is very difficult to forecast, right? So it's all over the place. You can't really pick out a signal there, can you? Now, solar power is also variable and uncertain, right? So this just shows the variability at different timescales. This is from a single location. You get aggregation benefits from having solar at different locations. And so you smooth out a lot of this high frequency variability, and you're maintained with still the diurnal cycle. However, you still have the diurnal cycle, right? You're not going to produce solar power at midnight. Just not going to happen. And so we have to be able to deal with those two issues in the power system. The third big difference between wind and solar power and conventional generation is that they are asynchronous. So that means that they don't produce at the same frequency as an actual motor, right? They're connected to the grid by power electronics. And this is both good and bad. The good part is they are very fast, right? You can tell them what to do, they respond very quickly, but you have to tell them what to do. Thermal plants, say you have a fault in the system, just react to it. They overproduce to keep the frequency high, and you don't pay for that, it's just expected. So we're going to talk a lot more about this aspect in terms of inertia when we get into one of the projects. So where are we in the US on the overall global landscape of renewable energy? Well, I mentioned that some places are trying to go toward 100% renewable energy. There's only 2 islands that I know of that are 100% renewable energy. So one is Tau Island, which is a very small island in the Pacific, and it has a load of 400 kilowatts peak or so. And so basically they built a really, really big PV plant and a really, really big battery. And they can afford to do that because they're importing oil otherwise to produce it from really far away. And so it's actually cost competitive for them. The other place is Iceland. And Iceland is all hydropower and geothermal power. And that's a little bit different. So that brings, those are more like traditional thermal generators. And so you don't have some of the same issues that you have with wind and solar there. A lot of these, so this graph shows the size of the system in terms of gigawatts, and then the percent of variable renewable energy, so here chiefly PV and wind. And you can see a pretty good trend here, right? You have these small systems that can go to higher levels, and then you get down to these bigger systems, and the levels are a lot lower, right? Part of that's just because these are massive infrastructure systems, and so there are massive costs associated with making a transition like that. The entire continental US is about 7, maybe 8% now. Western United States is 9%. Germany is about 20%. Denmark's about 42%. The island of Maui is about 35%. Now, there's something different here, and that's denoted by a star. So these are all parts of larger synchronous systems. So basically, you're artificially drawing a boundary somewhere, right? Maui can't call on Oahu in order to provide it with power if it needs to. These systems can. Denmark imports and exports power from Germany, from Sweden, from Norway. So does Germany does the same in the continental US. There's a political issue right now around Colorado going to 100% renewable energy. Colorado's in that same situation. If we need more power, we can always call up Wyoming, for example, and ask for more. Or if we have too much, we can send it to California. Can't do that in a system like Ireland, which is about 22% on an annual energy basis, and they get instantaneous penetrations of renewable energy up to about 65%. And that's where their system operator has set the limit right now because of inertial issues that they're trying to figure out. In Colorado here, we've gotten up to about 67% instantaneous penetration from mostly wind power. Okay, so I've talked about a lot of the different things that are happening in the system. We're getting a system that goes from large plants down to the customers, and now we're switching that. We're sending power back from the customers to the rest of the system as well. This creates things like bidirectional power flows that the system maybe wasn't designed for, have more voltage fluctuations, and I'll show you an example of that from my house later, and then more asynchronous generation. So all these things mean that we need more smart devices, and especially the communication systems that allow us to access them. And that's why I think that there's a great overlap here between the power network and communications networks as well. So we have very few sensors on the distribution grid in particular. And so we need new technologies that can provide the communications and control that we need to those devices, and we need to be able to do that in a very reliable and economic manner. Okay, so just one more thing. I'm going to be talking mostly about simulation today, different simulation of the power system. And so this is becoming ever more important. Because let's just say I want to test out a new technology. I can't just go install it, see what happens on the power system, and then if it doesn't work, cause a blackout, right? Because you have things like the 2003 blackout in the Northeast US. This put 55 million people without power for up to a week, and it was estimated to cost $10 billion in lost GDP. So you have to be able to test these things in silico before you can test them in the real world and before you can implement them. And so we have all these new technologies that are coming into the system. We have to be able to maintain our stringent reliability standards, and we have to understand that these are huge systems with large investments. And so we need to be able to do this process, and we can't, if we make mistakes, those are going to last a long time. So nuclear plants, for example, have a assumed lifetime of about 50 years. That's a big investment. Okay, so because of this, we need simulation models and computational tools that can predict the impacts of new technologies before they're actually implemented in practice. And this includes being able to detect things like cyber threats and where they might come from. And we need to be able to test those in silico before we see them in actuality in the real world. Okay, so enough background. Going to dive into one of the projects that we've been working on. This was funded by RPE and is called SmartDS, which we're creating synthetic models for advanced, realistic testing of distribution systems and scenarios. So this is something we at NREL led, and we're doing in conjunction with MIT, Comillas University in Spain, and then our industrial partners EDD and SIME. So this is something that was a 2-year project, is just wrapping up at the moment, and it's creating new power system data so that we can study these things. Why do we need that? Well, let's just say I want to go from my office at NREL up to my office here at CU, right? I can type it in Google Maps and I'm fine. Know which way to go, know if there's going to be traffic one way or another. That's the future power system. The current power system is like trying to do that using one of these little cartoon maps that you get in tourist locations, right? You can't see anything, you have no idea what's going on, you're going to get lost. And so the reason why is that a lot of the test systems we have today were created 30, 40 years ago. They are maybe for the distribution system a single feeder, so one line coming off of a substation. They're very small, so the most common test case is the IEEE 123 bus feeder. So that's tiny, that's nowhere near our real size distribution feeder. They're very limited in data. They were usually designed for one purpose, and we have a lot of new applications that are coming out that we can't use them for. And then they have almost no low voltage network secondaries. And I'm going to show you a little bit later why that's very important. Real distributions on the systems, on the other hand, have many interconnected feeders at a substation, and they have interactions between them. You have millions of nodes, you have substations, you have switches, you have controllers that are all not reflected here. And you have lots of low voltage wires, right? That last 20 yards, 20 meters of wire that goes from the little green box in your backyard to your house. We don't model that traditionally in power systems. That's a mistake. I'll show you why. Okay, so I want to play you a video. So if you pay attention for 1 minute the whole time, pay attention for this 1 minute now, and this video will show you everything about this project. And I'll try to talk through it, and then I'll go into a little bit more detail on some of it. Okay, so we're trying to create realistic distribution test systems. So we take a geographic area and we utilize open information about parcels and street maps, and then we build out our sub-transmission network. We also build out the substations that connect transmission and distribution. If we zoom in, we then build out the medium voltage laterals that we have, the single phase wires. We run put in our distribution transformers, run a power flow to make sure this is staying within voltage limits, and then include the secondaries and things like the capacitor banks and voltage regulators that make sure that you can actually operate the system within the specified limits. We also add things like reclosers and switches so you can do reconfiguration. And then we put on this a whole layer of different scenarios, of different loads, different demand response, solar power, things like that. And so this allows us to look at a lot of different scenarios of the impacts of DERs, full VAR optimization, optimal power flow, reconfiguration, and fault scenarios. All those are types of scenarios that the traditional test systems just won't allow you to do. Okay, so I know that was really quick. That was a 2-year project in 1 minute. But, got to go forward. Okay, what's the result of all that? Well, we've created 3 very large test systems that are open and publicly available. You can go to bettergrids.org right now, download any of these. So we have our small test system. Remember I said, the IEEE 123 bus feeder was a typical one? Well, our medium test system has 166,000 buses. So this is what a realistic city's distribution system looks like. This is what Boulder's distribution system looks like, right? This is Santa Fe as an example, but it's about the same size, about 38,000 customers. We also ran one for Greensboro, North Carolina with about 65,000 customers. And then we decided that probably wasn't big enough. And so we built the Bay Area test system. And so this is the entire Bay Area. This is just in comparison with Greensboro and Santa Fe. So we have 4.3 million customers. We have 10 million electrical nodes and about 2,000 separate feeders. So remember I said usually right now you run on one feeder. Well, this shows you the interactions of all those 2,000 different feeders. So this is a huge data set, publicly available at the moment. We don't expect people to actually run stuff on this yet, but we're trying to create a data set that will be good not only for the problems that we have now, but also the problems that we anticipate having in the future as well. Okay, so that was a quick overview of what we're doing in terms of creating data so that we can do better simulations of the power system going forward and understand the impacts of new technologies. Now I want to talk to you about a very small project that we just are sort of going through right now, and it's on the potential threat of smart devices for grid security. Okay, so this is the cybersecurity aspect, and I want you to take a leap with me on an assumption, okay? So there's lots of new Internet of Things connected devices throughout the system, right? We've gone from, in 2004, about 500 million to we're projected in 2020 to have 50 billion of these. One of these types of devices is the Nest thermostat, right? There are different types of smart thermostats as well, but the Nest and other smart thermostats are already installed in about 15% of homes. So that means you can control gigawatts, large amounts of load. So what happens if Google servers get hacked and somebody can control those? Let's find out. So in order to know that, you have to know what the homes are doing, right? In the US, especially in the summer, a lot of the load is based on air conditioning. And so what we've done is at NRO we have a group called the Commercial Buildings Group, and they have a tool called, we have a Commercial Buildings Group and a Residential Building Group, and our Residential Building Group has created a tool called ResStock. So this is highly granular simulations of different types of residential houses. So you can look at those houses and you can simulate, okay, if I have a smart thermostat, for example, and I want to lower the set point of my thermometer and all those, how much extra energy does that take up, right? How much more power do I need in the system? So I can do a high resolution analysis of the load in the system and then see how that changes, know how much of that is coming from AC, for example, and then see what happens if I change that. And so what we've done here is we've taken 216 different weather file locations throughout the US, and we focus here actually on the western interconnection of the US, and so you have about 75 different weather locations, because weather drives load. So temperature, humidity are the largest inputs into load, along with what day of the week it is. And so we've taken that and we've mapped that over to a model that we have of the entire western interconnection of the US. So that's about 3,000 nodes at the transmission level. So this is a database that was created by the Western Electricity Coordinating Council in order to study the impact of events on the system. So what happens if the largest nuclear power plant in the Western Interconnection, Palo Verde, here in Arizona, goes out? You lose 3 to 4 gigawatts of power instantaneously. And so you can liken that, some of the threats that you have from residential air conditioning being able to be manipulated to a large event like that. And I'll show the impact of that here in a second. Just a little bit more data about how we combine that, those two data sources. So we've taken the weather files and we've basically mapped them to each of the nearest nodes in the system. So we've aggregated the load. So we could say on this day in 2014, 25% of the load was residential air conditioning, given the weather conditions that we saw then. And so we can then apply that to the AC model load that we've utilized for the power system simulations. And then we can ensure that we're getting an accurate modeling of what the demand just from those devices would be. Okay, so I'm going to talk about a power system simulation here. So this was done in a tool called PSLF. So this does power system dynamic simulation. So you're looking at the millisecond response of the power system to changes. What we've done is we've taken AC load and we've put it as a fourth motor within a sort of aggregated load model. So this includes lots of different types of motors, power electronics, static loads, things of that nature. This allows us to look at both the real and reactive power components, because that's very important for things like voltage stability of that system. And then we've taken this PSLF model that we've used previously for some other studies, and we took the heavy summer load case. So this is the case that everybody plans to. You have to be able to meet load on the hottest day of summer and have a margin. You also need to be able to, on that same day, survive the largest single contingency, which is that Palo Verde nuclear reactor outage. Now, that's happened multiple times. They actually built a double line to Palo Verde, and they put them not too far apart, and they thought, well, at least we have this, we'll never have to worry about a contingency there, both lines won't go out. And within a couple months of them doing that, a helicopter just happened to run into both the lines, and it tripped out. So this is a credible contingency. Okay, so we took this date for August 25th, 2012 at exactly 1:20 in the afternoon. And so on this system, you have approximately 185 gigawatts of load at that moment. This was done with what we use as our base case, and that means this has a very low wind and solar penetration. Remember the inertia that I talked about earlier? As you put more wind and solar on this system, the inertia is going to go down, and so the responses that I'm going to show are going to be even greater. And so this is basically a very conservative assumption that says even in an old power system, that has this naturally provided inertia, you're going to experience these issues. So as we add more wind and solar, this is going to become even more important. Okay, so a couple more assumptions just around the simulation, and then I'll promise I'll get into the results. So we are looking here at the residential AC loads, and we've broken it down into different parts of the system, Arizona, Colorado, for example. And this is how much AC load you had on the system at that time. So in total, about 11 gigawatts of load. It had a maximum potential of about 26 gigawatts of load. So that means, at any time, roughly half of the AC was on, right? This is the hottest day of the summer. That makes sense because your AC has, you can't just run it nonstop. It has an on-off duty cycle that it has to run. And so we looked at three different sort of assumptions in terms of controllable things. Let's say, 10% of the total AC load was controllable. That means you'd have 1,150 dispatch AC, and you could, if you wanted to control that, put that up to about 2,600. Let's say you were able to control 30% of that. Remember, right now, we already have 17% penetration of smart thermostats. So right now, if you could control all those, this is where you would be. You can imagine in 2 or 3 years, we're probably going to be here very quickly. Okay, so for that simulation, we took a percentage of that load, and we assumed that we can do with it whatever we want. At the first second of the simulation, we turned it all off. 60 seconds later, we turned everything on. Now, you could imagine different patterns that would have different responses in the system, but this gives you basically the largest single instantaneous change in load on the system, right? And so you could posit that this would probably have one of the largest effects. And then we keep running simulation to see how the power system responds to that and what happens. All right, so here's the 3 different cases: the 10%, the 20%, and the 30%. A couple things you want to know about power system frequency. So we run at 60 hertz here in the US, not 50 hertz, like in Europe and some other places. And you automatically, so your band, your sort of dead band on where you want to control things goes from 60 to 60.2 hertz. This is an over frequency event, and you start shedding load to protect equipment at 60.2. And at 59.8, you also start shedding load. So you have a lot of other remedial actions that happen in between, but this is bad. This is really, really bad when you hit 59.8. People get fired for this. So you have 10% of your load, and you turn it all off. Because you have way less generation now, your frequency actually goes up, right? You go along at 60 seconds, you now turn that all on, your frequency drops. Now, the system is able to recover. So in frequency studies, you look at the nadir, and then you look at how fast, you also look at the settling frequency and how fast you respond to that. And if you had that 30% load, you would drop down below 59.8. You would be shedding load because of that. Now, remember, this is without a lot of wind and solar in the system, right? So if you added more wind and solar, this is going to go even deeper in the current way that we operate the system. But there are things you can do. The good news is wind and solar can help arrest this. The bad news is we don't require them to do so right now, and we don't have any markets that incentivize them to do so. And so that's a huge area of opportunity. We can have wind plants or solar plants, let's just say, hold back 5% of their generation. So don't produce as much as they were going to. And then when something like this happens, they have the room to sort of mitigate it and go against it. But that's where we need policy. That's where we need either regulation that requires them to provide that service, or we need markets that incentivize them to provide that service. So this is a scary thing for the power system generator. And I haven't even mentioned yet the distributed generation and the impact that would have. Okay, one more thing that's kind of scary, but also kind of cool. If you do that same thing, and you turn off all your AC, you turn it back on, so I like to say frequency is global, voltage is local. So your frequency should be the same across the entire system. And most of the time, that's a very good assumption. When you have something like this happen, that starts to be not so good of an assumption. And you start to have, for example, in the Western Interconnection, you have a connection to Canada and Alberta. And in this case, you start to see the frequency in Alberta deviating from the frequency on the rest of the system. So this has the potential to cause system separation, which is definitely not something you want. You'd probably black out Alberta in a situation like that, all of it. So that's scary. We've seen things like this happen in the past. Last year, the Western Electricity Coordinating Council and Peak Reliability saw a situation where 2 of the tie lines to Alberta were running, and there's 3 total, and the other one was down for maintenance. One of them tripped, and you had a situation exactly like this happen. And so, this is sort of the worst case nightmare for a power system operator in that case, because your reliability is going to go down. The scores that FERC is assessing you on is going to go down. Okay, so these are just some preliminary results that we've got from this study that I'm very excited about. And I want to talk a little bit about the conclusions, what we can learn from this, and then the next steps. So this, the ability for a cybersecurity event getting control of demand response, or maybe, let's say, solar PV generation through an aggregator such as, SolarCity/Tesla that owns all these things, or Tesla owns a lot of, behind-the-meter batteries. There's a potential for that, and that could have credible contingency implications. So this could be as large or larger than the largest contingency that we've planned the system for right now. So that's something we should worry about. There's potential for under-frequency load shedding and system separation, which power system operators do not like whatsoever. And then we do need to do a bit more detailed analysis on this to fully understand the implications. I want to talk here about the sort of next steps on what I think we should do with this. One of the things we need to do is explore the cascading events. If you start to have voltage issues or frequency issues, something trips off, and then something else trips off, and then something else trips off. And that's how you cause blackouts like that 2003 Northeast blackout. By doing this, you can identify weak points in the transmission system and understand where we need to reinforce the system against these types of contingencies. This simulation doesn't include the impact of distributed PV and in particular IEEE 1547. So long story short on 1547 is the interconnection agreement to connect PV into the grid. When it was first created, they said, as soon as you see something wrong, turn off. And the reason for that is if the system went out, they didn't want linemen going out there and electrocuting themselves. Now, we've gotten more wind and solar on the system, and so about 4 years ago they said, well, you can stay on if you want to during these times and try to support the rest of the system. Just this year we passed 1547-2018, which says now wind or distributed energy resources, in particular solar, have to be able to respond to some sorts of issues. So you have to have frequency and voltage ride through within certain bands. Now, if you go outside those bands, for example, going under 59.8, that no longer applies, and your load that you thought was there may go up even more because the distributed PV that you don't see could go off too. And so as we include more distributed generation, this is going to multiply the impacts of a frequency event like I showed earlier. Finally, more on the cybersecurity side, I think it's very important to be able to create techniques to identify when an event like this might be happening, and then figure out what some of the mitigation measures might be. Okay, just to show the impact of sort of 1547, we ran a simulation a while ago where we looked at if 1547 said get off and you had a pretty large amount of distributed PV on the system, what would happen to your frequency. So this is, the blue is the sort of normal case of a large contingency, and note you're all the way down to 59.4 here. If the distributed PV kicks off, you're down at 58.6. That is unheard of. That is virtually impossible. In the current, well, it's not impossible, it just never happens because everything shuts down before then. Okay, so that shows the impact that that could have. This was on a WEC contingency case, losing all 3 of the generators at Palo Verde, so that's 4.1 gigawatts. And we're going to have, by 2020, about 32 gigawatts, 32 compared to 4 of distributed PV. So we need to figure this out. Okay, now, a personal note here, and why distribution systems modeling and why all these impacts from distributed PV are so important. This is the Xcel Energy model of the feeder that serves my house. So I live in Golden, and here's the substation. And the feeder goes out, and my house is around here. Now, I have 6 kilowatts of PV on my house. So do all my neighbors. That creates some funny things. So remember I said voltage is local, frequency is global. You want to keep voltage within bands just like you want to keep frequency within bands. So voltage you want to keep between 1.05 per unit. So take the voltage, divide by the nominal rating, so 120 or 240 volts in this case, and then 0.95 per unit. Now, if you have PV and it's a sunny day, no problems, not a cloud in the sky, we get a lot of that here in Colorado. The system, as it operates now, does a pretty good job keeping voltage within its bands. So these are actual measurements from my house. And you can see when they take corrective actions. Do they use a capacitor bank? Do they do a tap changer? Things like that. When you get a lot of PV variability, Xcel's already going outside of those limits. Now, that has big implications. So, as an example, I think this is why the cap bank on my AC unit blew. Because of this, exactly. And that's why I started looking into this. Now, I was talking before about modeling secondaries and how important that is. The reason why that's so important is the measured data shows a PV variability at my house of about 5 volts during some of these events. Right? Remember, your limit is, so that's about half of your limit between nominal and the upper limit. If you don't model the secondaries, if you don't model that last 30 meters of wire to your house, that's where you get the biggest losses, right? Or the rise if you have PV. And so the utility only sees about a 2-volt increase during that event, not the 5-volt increase, which means most of the time I'm operating at my house above the level, which means if I have a, let's just say I had a Tesla and I was charging it, I could expect shorter battery life. I can blow capacitors on my refrigerator. You can get a lot of equipment damage. You could even damage your PV inverter as well from things like that. And this is because we don't have visibility into the distribution system. We don't have the sensors, and we don't have the communication systems that can bring that information back to the utility so that they can actually use that to control the system better. Okay, just to wrap up, the power system is rapidly evolving, and so we need better data and more advanced simulation tools in order to understand how we're going to design and operate a sustainable, economic, and reliable future power system. We need these tools to be able to study the impact of new technologies before they're actually deployed. And we need them as well to be able to understand some of the advanced security threats that we have in this new system and how we can prepare for them. I've been really lucky at NREL to work with a number of fantastic folks. And so I would like to thank them for their contributions to this. And I would like to thank you for your attention, and I'd be happy to answer any questions.
So we have time for several questions. And Professor Bri has graciously indicated that, yes, indeed, and I see several hands, and so let me start with the student, and then I'll go to people who look like, okay, well, you understand.
You talked about hacking nests and things like that. What if you were to hack the power generation systems? Wouldn't that be much more detrimental to the power system?
Yeah. So the traditional generators are kind of on the lookout for that, let's say. Because you have one big plant, let's say it's a nuclear plant, it's a gigawatt, they can put some, time and effort into protecting against that. Now, do they do a great job of that? I've read some stories recently that make me think otherwise. But it's a single point event. With the new systems, like the PV on my house, right? If they get into that and they get into a bunch of other ones, it's distributed. And so it has different implications, but they could be even worse.
I'd just add a comment. Talk to the people in Colorado Springs. They get something like 300 attacks a day trying to hack into their system to protect. And there are certainly serious people that would like to figure out how to break that system because it controls the missile system for defense system. So there's just in terms of cybersecurity aspects of it, there is reason to be very concerned about cyber attacks on that.
Definitely.
Things.
So we've seen a lot of stories coming out publicly about systems that may have been compromised or were attempted to be compromised, and that's just the tip of the iceberg.
So I have a question. What are we as people supposed to do? I mean, we're not energy experts. We're just technology, cybersecurity, and policy people. That's all we are, and we can't predict the future. I mean, what do we do? How do we survive?
Well, you are technology, cybersecurity experts, and that's what we need, right? So I think the biggest thing is we need to increase understanding of how the power system works from other fields, right? There's a lot of great stuff that's happened in cybersecurity that maybe hasn't been applied to the power system yet. Right now, pretty much everyone just flicks a switch and assumes the light's going to come on, right? You don't look at all the things necessary in order to make that happen or understand the implications on the economy, for example, if that doesn't happen. And so we need folks who do know things about cybersecurity, who do know things about policy, because I think in both the cybersecurity and the energy area, that policy, the ties between the technical aspects and the policymakers is, let's just say, less than ideal. And so we need folks that can speak both those languages so that we can implement smart policies that make sense for the energy system and can protect against things like that.
Any other questions, comments, assertions? Let's thank our speaker one more time.
Well done. Okay, so every time I hear one of these lectures, I get scared. I get more and more frightened because